The next technique for solving differential equations that we're going to learn is called separation of variables. And this is a technique that really should be applied to nonlinear differential equations. In the previous lesson, we learned how to use integrating factors to solve linear differential equations, and that really is the preferred method when solving linear differential equations. This new method, separation of variables, will be familiar to some of you, and you might be tempted to use it for all sorts of differential equations, but you should really stick to using it for nonlinear differential equations. Because while it is a good technique, there are a lot of pitfalls to this technique. There are a lot of possible errors that you could make. And so you really should only use this technique when you have to. So in order to set up the technique of separation of variables, I would first like to motivate it with a very simple model. And this is the simplest nonlinear model that I could come up with. And it uses what's called Torricelli's law. And according to Torricelli's law, the rate at which water flows out of a cylindrical tank of radius r from a small hole in the bottom is proportional to the area of that hole, A, and the square root of the height of the water in the tank. So what I want to do is I'm going to draw a tank that's a cylindrical tank, and it's going to have a radius r. And I'm going to imagine that there's a little small hole in the bottom of this tank and that there's water flowing out of that hole. And the cross-sectional area of that little hole is A. Now I'm going to set up a y-axis here. And the y-axis is going to give me the height of the water at a particular moment. So let's say that that is the height of the water, okay? And so that is the height, say, y. And so what's happening is water is slowly draining out of this tank, and the rate at which water flows out of the tank is proportional, like I said before, to the cross-sectional area of the hole and the square root of the height of the water. So let's take those words and let's turn them into a differential equation. So we'll start with the rate at which the water flows out of a cylindrical tank. So that is the rate of change of the volume of the water, dV dt. Now, water is flowing out, so we're seeing a decrease in water, so we're going to imagine that's negative. And then it is proportional to, well, it's proportional to, so that means it's a constant times, and it's actually proportional to two things, the area of the hole, A, and the square root of the height of the water. So that's proportional to A, okay, it's times A and times the square root of the height of the water, which we'll call y. Now, immediately you should see that this is an equation that describes the rate of change of the volume, okay, but it's in terms of the height, the current height, which is y. So we need to think about, well, what is the volume? The volume V is going to be pi r squared times the height of the water, which is going to be y. So there's actually a relationship between V and y. So that means dV dt we can think of as being pi r squared times dy dt. And that is equal to negative k a square root of y. So what we're going to do is we're going to divide by pi r squared, and we're going to make a new constant. I'm going to call it c, and that's going to be ka over pi r squared. So if we divide by pi r squared, we get that dy dt is going to equal minus c times the square root of y. Now there's an initial volume v sub 0, and so we've got to relate that to the initial height. So y of 0, the initial height, should be v sub 0 divided by pi r squared. Okay, it's the initial volume divided by the area, the base area, pi r squared. Okay, and we're going to call that y sub 0. And so what we're going to do is we're going to solve this system. dy dt equals minus c times the square root of y, and y of 0 equals y sub 0. Now, this is a nonlinear equation because of the square root of y. Okay, there's not a linear operation that's being done to y. Okay, so that's going to require us to use a different technique. This technique is going to be called separation of variables. I'm going to run through the technique first, and then I'll talk a little bit about why it works. Okay, so often what you do is you write dy, and then you multiply by this factor dt. So we know that dy dt is not a fraction, okay? It represents a limit, but this is kind of a shorthand for the technique. So we'll multiply the right-hand side by dt. And in fact, that will give us a minus c square root of y dt. Okay, and then what we want to do is separate the variables. So we're actually going to move the square root of y over to this side. So I'm going to divide by square root of y. Okay, so I'm going to get dy over square root of y is equal to minus c dt. So what I've done is I've separated the variables so that all the y's are on one side and everything that has to do with t is on the other side. Now, it's just a choice to leave the constant c on the right-hand side, but you'll see that that's kind of the easier choice to make. Okay, and now what I'm going to do is I'm going to integrate both sides. Okay, so I'm going to integrate the left-hand side from y0 to y, and I'll need to use a different variable here, so I'll do dx over square root of x. And then I'm going to integrate the right-hand side in t, so it's minus c times the integral from, we'll start at 0 and go to t, and we're going to integrate, well, what's left is just dt, but I need to, again, use another variable, so I'll use ds. Okay. Now, the antiderivative of 1 over square root of x is going to be 2 square root of x. I'm going to evaluate that between y0 and y. And then minus c, and then s, again evaluated between 0 and t. Okay, so this is going to give us 2 square root of y minus 2 square root of y0 is equal to minus c times t. Okay, so at this point, I'm going to divide everything by 2. So I'm going to divide out everything by 2. And then I'm going to solve here for square root of y, which in this case is equal to minus c over 2 t plus the square root of y sub 0. So that tells me what y is. Y in this case is minus c over 2t plus the square root of y0 quantity squared. And so I've now solved this differential equation. And I encourage you to substitute back into the original differential equation to indeed show that dy dt is equal to minus c times the square root of y. You can immediately see if you plug in 0 that y of 0 is y sub 0. Okay, so we've solved this, separable differential equation. Okay, well, let's look a little bit at what the solution looks like. Okay, so let's look at a specific example. So let's consider the example where c is equal to 3 over 20. Maybe we're thinking about that the radius of this cylinder is 20 the area of the base of the cylinder is 20, and maybe the cross-sectional area of the hole is 3. That way c is 3/20. Okay, and then y0 in this case we're going to let be 4. Okay, then y of t in this case is going to be, let's see, minus c over 2, so that's minus 3/40 t plus 2, okay, because y0 is the square root of 4, or sorry, the square root of y0 is the square root of 4, which is 2, okay, and we're going to square that. Okay, so y of t is minus 3/40 t plus 2 quantity squared. So y is a parabola. And you notice that I've graphed the parabola for you. So what is going on? So we're starting at 4 here, okay? And water is draining out of the tank. And it keeps draining out of the tank until you get to, there's no water left in the tank. And then, of course, once there's no water left in the tank will spontaneously just fill with water again. That makes sense, right? That doesn't actually make sense, does it? It doesn't make sense that the water would start to spontaneously fill, the tank will start to spontaneously fill with water again, okay? There's some point here, okay, where the water has completely left the tank and there's no more water in the tank. The height of the water in the tank is 0, and at that point, water should not start filling back up in the tank again. You'll notice that the solution matches the slope field all along here. But you'll see that the slopes don't match the solution on that side. So the solution is not valid anymore. Okay? Well, when is it not valid anymore? It's not valid when we go beyond the time at which the height is 0. So if we solve this expression right here, if we set it equal to 0, we can see that the solution is only valid for t less than or equal to, say, 80/3. If we go beyond that, then the solution is no longer valid. It's no longer physically valid. Okay, so you can see that this method is a little bit problematic because it led to a solution which is only valid for a certain amount of time, at least physically, and then no longer does it match the physical description. And this is the kind of problem that can occur when you're dealing with nonlinear differential equations. You might find that the solution isn't going to be valid for all time, that there's going to be some times where the solution is not valid. And we're going to talk a little bit more about the existence of solutions and the uniqueness of those solutions in the next lesson. So let's go back and let's talk a little bit about why this technique of separation of variables worked. Why is it that I can multiply by dt here when I know that dy dt is not just simply a fraction? Why does that work?